So this is an Abaqus tutorial video to complement the 2071 Mechanics of Solid Materials class taught by Professor Lalitanand at the Mechanical Engineering Department at MIT. And this is the first tutorial video where we're going to look at this problem of a thick-walled cylindrical pressure vessel. So this is in the course text, this is section 9.2. So this is the problem setup that we are going to work with. A thick wall cylinder with an internal inner radius of 100 millimeters, an outer radius of 200 millimeters, and a height of 200 millimeters. And it's subjected to an inner pressure of 50 megapascal and outer pressure of 30 megapascal. So what we're going to do in our simulation is exploiting the symmetry of this setup. So we're going to perform an axisymmetric simulation. So this, in an axisymmetric scenario, you would model this cylinder as this simple rectangle. So this rectangle has a one of its walls 100 millimeters from the axis of symmetry here, and the outer wall is at 200 millimeters from the axis of symmetry. And this is where on the inner face we apply the pressure of 50 megapascal. On the outer face we apply this pressure of 30 megapascal. And we're first going to consider plane strain condition, where in the vertical direction we do not allow for any motion of the top or the bottom face. So it's constrained in the vertical direction, although it can still expand and contract in the radial direction. And as for the material, we're going to take the pressure vessel to be made of steel. We'll model the steel as an elastic, perfectly plastic material with material parameters representative of a structural steel alloy with that is to say a Young's modulus of 200 gigapascal, a Poisson's ratio of 0.33, and a yield stress of about 300 megapascal. So other common material choices in for pressure vessels include aluminum and titanium, which are generally, because they have a higher specific stiffness or specific modulus, which is the modulus over the density. So they are preferred in weight sensitive applications such as in the aerospace industry. But for this problem, let's just consider our pressure vessel to be made of steel. So given all of this, I'm going to move into open up Abaqus CAE and open a new model database with the standard explicit. Okay, so the way Abaqus is designed is in terms of these several different modules. So you see this drop down list right at the top. So you have these different modules: part, property, assembly, step, interaction, and so on. So when we want to model a boundary value problem in Abaqus, we need to step through each of these modules one by one. As we go along, I'll show you what we do in each of these different modules. So the first module is this module called part. This is where we're going to sketch the setup that we're going to simulate. So in this case, it would be this rectangle that we need to sketch up in the part section, because we're going to do an axisymmetric simulation. Okay, so first I'm going to click this menu icon here, which says create part. So I'm going to hit create part, and this is where you name the part. I'm going to call it a cylinder. Uh, and because we're doing an axisymmetric calculation, we need to tell Abaqus that we're doing an axisymmetric calculation. We want a deformable body, and we need to give in its size. So Abaqus by itself does not really have any units. What we need to do is to give it a consistent set of units. So for this problem, we are just going to stick with SI units. So since our cylinder has a rough dimension of about 200 millimeters, so you only need to supply the approximate size here. So I'm going to say 200 millimeters. So I'm going to say 200 E minus 3. So that's what I entered into this box here. And once I do that, I'm going to hit continue. So if I hit continue, you'll see this sketch window appear. This is where we need to sketch our part. So this y-axis in this axis symmetric setup, this y-axis is the axis of symmetry. So we need to sketch our part with keeping that in mind with respect to that axis of symmetry. So what I'm going to do is first mark out the two diagonally opposite points of the rectangle that we need to sketch. So to do that, I'm going to first click this icon which says create an isolated point. So you can use that menu to create points. So let me click it and then I'll show you what happens. So once you hit the create point, uh, at the bottom here, you can enter the x and y coordinates of the point as you require. So what I'm going to do here is enter this. First, I'm going to enter this bottom left point, which is the x coordinate is 100 millimeters, and the y coordinate I'm going to take it to be 0 here. That's the reference I'm going to take. So then I'm going to enter. You see here I'm entering in this box 100 e minus 3 for the x coordinate and 0 for the y coordinate. If I given the coordinates and hit enter, you see this point appear here. That's the left bottom vertex of the rectangle. And now I'm also going to create the right top vertex, which is this one that has an x coordinate of 200 millimeters and a y coordinate also of 200 millimeters. So let's go ahead and enter that again in this dialog box right at the bottom. I'm going to say 200 e minus 3 and 200 e minus 3. Okay, so that created a point right here. And now what we need to do is to sketch a rectangle. So there are several different options within the sketching module here. So I encourage you to explore all of these various options. But for now, we have a very simple tool that we can use that Abaqus provides us, which is this option of creating a rectangle. So if I hit this option here, which says create a rectangle, all I need to do is click on two diagonally opposite points, and the rectangle is going to be created. So since I've already marked out the diagonally opposite points using the create point menu like we just did, I'm going to first click on this bottom left corner, and then my second click is going to be on this top right corner. And once I do that, this rectangle is going to be created. So yeah, just as simple as that with an Abaqus. So once I'm done with that, you can also create other rectangles, but here we also have we are happy with this sketch. This is the part that we want to work with. So then I'm going to say cancel procedure because we are happy with whatever it is right now. And then the menu is going to say sketch the section for the planar shell. I've already done that. So because I'm content with what I've already done, I'm going to hit done. And that creates this particular part. So with this, we are actually done with our part module. And before I move to the next module, let's just quickly save our part, save our CAE job. So I'm gonna go into file and say save. I'm gonna save it as cylinder thick. So yes, so as I said, we are done with the part module. Next, I'm going to move on to the property module. So this is where we're going to feed in what our part is going to be made of. We decided that we're going to work with a steel thick wall cylinder. So let's create the material properties for the steel. So what we need to do first in this property module is to hit this create material dialog box right at this top left the top left option in that menu. So I'm going to say create material. Then this dialog box is going to pop up where first it asks you to name the material. I'm going to call it steel because we are making a that's the material that we're going to work with. And then once I say steel, we are going to we need to say that we're modeling it as a linear elastic material, right? Because that's what we decided. If I go back to the PPT, that's what we decided. We decided to model it as an elastic, perfectly plastic material. So I go back to CAE, and under the mechanical menu, there's this option of which is elasticity. So I'm gonna go in there and just say the first option, elastic. So once I hit that, uh, by default it's an isotropic elasticity. That's what we're going to work with here, and it has this property window here where you need to enter two properties, the Young's modulus and the Poisson's ratio. So we decided to use these values, 200 gigapascal for the stiffness and 0.33 for the Poisson's ratio. So I'm going to go ahead and enter these values in here. So I'm going to say 200. Remember, we are working with the SI units. So I'm going to say 200 E9 for the gigapascal. And for the Poisson's ratio, I'm going to say 0.33. So, so that's all I need to do for the elastic part. But we also wanted to model it as an elastic, perfectly plastic material. So then what we need to do is uh, we also need to add plastic properties. So I'm again going to select this mechanical option here. And then under that, now I'm going to define the plastic property. So I'm going to say under plasticity, I'm going to select just the first simple option, plastic, right? So then it asks for the yield stress. So here is where you can, if you have a strain hardening material, you would enter the various values that you measured or that you're aware of the material. But since we are modeling it as a perfectly plastic material, so then we're going to just given the values that we intend to. So here we decided a yield stress of about 300 megapascal. So then I'm going to say 300 E6 again. Remember SI units at a plastic strain of 0. And then if I hit enter, it's going to create this second row. So because we decided to model it as a perfectly plastic material, so then this yield stress is going to be constant. So I'm going to again say 300 E6 at a plastic strain of 1. So just so that you given two values, so it's going, Abaqus is going to interpolate it linearly between those two values. And because we have given a constant yield stress, that will amount to a perfectly plastic material at this yield stress of 300 megapascal. So yeah, so once I'm done with this, I've also defined the plastic behavior of the material. You see in this space here, you see we have the elastic property for steel that we have defined, which is 200 gigapascal and 0.33 Poisson's ratio. And we've also defined its plastic properties as a perfectly plastic material yielding at 300 megapascal. So that's what we wanted to do, just the elastic and the plastic parameters. And once we are done with that, I'm going to hit OK. Yes, so we have created the material now, but we still have to assign that material to this part that we just created. So to do that, we still have two more steps. The first here is this option right below the create material, which if I hold my cursor mouse over that, it's going to say create section. So that's the menu that we need to work with right now. So I'm going to go ahead and click this and say create section. Let me call it a steel section. And then it's a homogeneous body, so it's a homogeneous section, a solid body, and those are the default options. So I'm happy with that. I'm going to say continue, and then this dialog box is going to pop up. So you have the options of selecting the different materials. Here we only created one material, which is already been selected here, steel. So I'm just going to leave it as is. Plane strain, this is an axisymmetry calculation, so the plane stress or strain is not relevant for now. So everything is already pre-selected here, and I'm happy with it. So I'm going to say okay. So then a section has been created. The next thing is to assign this section to our part. So right below the create section menu, there's an assign section icon, which I'm going to click next. I'm going to say assign section, and the instruction here says select the regions to be assigned a section and create a set. So since I'm going to select all of this body as the set, I'm just going to go ahead and call it all. And then I need to select the set. So I hold my cursor over this part, and then that's highlighted. So if I click on it, it's going to highlight the entire body, which is what we want. We want the entire body to be to tell Abaqus that the entire body is made of steel. So once I'm happy with selecting the body as well as naming the set, then I'm going to go ahead and enter and go ahead and click done. So then this dialog box pops up, and it's going to ask you what type of section it is. We only defined one section, which is a steel section, and that's what it's selected by default. So we're happy with that. So everything else looks good. So I'm gonna go ahead and say okay. So you see now Abaqus has been told that this section that this part that we drew out is actually made of steel. So then we are done with the second module, which is the property module. Let me quickly just save, uh, and let's keep continuing. Let's go to the next module on the assembly. Okay, here if we had if we are modeling uh, certain geometries where which would involve multiple paths which interact with each other, then this is where you'd create the different paths in the earlier sections and then bring them all together here. But since right now the problem we are looking at has only one part, which is the cylinder, so there's the assembly is all we need to do is just bring that part that we created, bring it into the assembly. So to do that, uh, you look at the this icon right at the top left, which says create instance. If I hold my cursor over it, so that's what we're going to do. So I'm going to click on it and say create instance. I'm going to select this part cylinder that we just created. We don't have any other parts. So this problem we're just working with one part. So so the cylinder is created, selected, and I'm going to go ahead and say okay. And that part has now been brought into this into the assembly that we're working with, and we are actually done with the assembly module. Okay, so I'm going to keep moving along our module tree, which is the next one is the step module. So let's go into the step module. And here is where you create a step. So let me go in here and then show you what all Abaqus can do, and then I'll talk about it as I go along. So yeah, again, the top left icon here says create step. That is, which is what we want to do. So then it asks us to name the step, and it has these different procedure types. So let me first go ahead and name the step. I'm going to call it, because we're going to apply a pressure, I'm going to call the step, I'm going to call it pressurize, because that's what we're going to do to the cylinder. So Abaqus can do several different types of calculations. You see this, you can do a coupled temperature displacement. That's how you would model some thermoelastic problems. For example, you could do coupled thermal electrical structural. So that's you can solve for the temperature, the electric potential fields, as well as the structural or the mechanical displacements within the body. You can do all of them simultaneously. So Abaqus has these several different options. But here we're going to do the simplest, the static. We're just doing a static analysis. So I'm going to go ahead and say static general. That's the kind of step that we're working with. And as I said here, I named the step pressurize. So once I've done that, I'm just going to go ahead and say continue. So then this dialog box pops up. So this is this is all data about the step that we just created that we need to enter. So this first one, time period, is the total time for the simulation. So by default it says 1. uh, so the total time itself, because we're doing a static analysis here without, and we're not going to do any have any inertia for the body. So uh, so the total time itself is not really very relevant, but I'm going to go ahead and change it to, just to show you, I'm going to change it to I'm going to say we're going to do this calculation over a time period of 100 seconds. So what we're going to do is, as I'll show you in the subsequent steps, we'll increase the pressure from 0 to the actual value that we need over this time period of 100 steps. So that's how we're going to model uh, our calculation. So I'm going to say the total time period is 100 seconds. Remember, we're working with SI units, so 100 by itself means 100 seconds. And if I go into this next menu, this was the basic menu. If I go into this incrementation, it has these different fields. So this is maximum number of increments. So this is as Abaqus is going to solve solve the problem that we have set up. It's going to move step across time. So this is it would take several increments to step across time. So we can tell it what are the maximum number of increments. So if Abaqus takes more than a certain number of increments to go from 0 to the total time that we supplied, which is 100. If it exceeds this particular value that we entered here, then the calculation is going to stop, and Abaqus is going to kill it. So what we typically want to do is give it a reasonably high value, just to make sure that we give it enough steps for it to go from a 0 to where we want it to go to. So I'm going to go ahead and say 1000. uh, an increment size, I'm going to say our total time step was 100. So if we want to look at what happens as we keep increasing the pressure step by step, so let's assume we want to look at least 10 different steps in our final results. So then, because we have a total time of 100, I want the step sizes to be preferably about 10. So I'm going to go ahead and say the initial step size that Abaqus should take is 10 seconds. The minimum is the minimum that you allow, because sometimes it might be difficult for Abaqus to take really large time steps. So it might end up taking smaller and smaller time steps. It might cut, the solver itself might cut back. So we're going to leave it at about 0.001, which should be sufficient for this problem. And the maximum time step that I'm going to allow, that one also I'm going to restrict it to 10. So then the idea is to be able to look at the the stresses at times of 0, 10, 20, 30, up to 100 seconds. So that's why give it a increment size initial of 10 seconds, a maximum of 10 seconds. And that's all we need to do. We just need to play with the basic and the incrementation menus, and we have already done that. I'm going to go ahead and say okay. So then this step has now been created. And let me quickly save our what we're doing. So then we are also done with the step module here. So the next module that comes up on the list is interaction. So typically, if you have problems where we have contact between, say, two different bodies, then this is where you would impose those constraints. So you have these different options of creating an interaction and creating a constraint. So this is where you do all those constraints. You define how different bodies within your assembly interact with each other. But in this particular case, as we have seen already, we just have this one part. It doesn't have to interact with any other part. So this interaction module is not relevant to what we're doing right now. So I'm just going to skip over from the interaction module to the next module, which is the load module. Okay. So this load module is where we're going to give it all the boundary conditions of the problem that we're looking at. So let me go back to the presentation. So remember, these are the boundary conditions that we need to give it. So the boundary conditions, the displacement conditions by themselves are no vertical motion for the bottom as well as the top edge, right? And then we also need to tell it that there's a load on the inner surface of 50 megapascal, a pressure, and then there's also a pressure on the outer surface of about 30 megapascal. Okay, so let's go back to the CAE, and what we're going to do is first create the displacement boundary conditions. To do that, we go to this the second row, which says this menu option, which says create boundary condition. If I hold my cursor over it, so that's what we're going to do first, and I'm going to click on it, and it's going to pop up this dialog box. So again, it asks for a name for the boundary condition. So let's the first one, let's do the bottom surface. So I'm going to say bottom fix. So we're going to fix it in the vertical direction. So I'm going to call it a bottom fix. And typically what you would want to do is impose the displacement boundary conditions actually in the initial step. So the step in this drop down menu here, you see an initial step and a pressurize. Pressurize is the step that we created. Initial is the one that's default for across all Abaqus problems. That's something that Abaqus already creates. So what we would like to do is to actually impose all our displacement boundary conditions right at the initial step, and then that's automatically going to be carried over to the next steps. And when we do our loads, as I'll show you in a couple of minutes, we'll do that load in the pressurized step. Okay, so then I'm going to go ahead and say step initial, because now we're doing the displacement boundary conditions. So I'm going to say bottom fix the displacement boundary condition, impose it in the initial step. It's a mechanical kind of a boundary condition. So this mechanical option here is right. And then there are these several different options. So fixing the bottom surface here actually can be done with at least three of these or different sub options that we have for creating the boundary condition. But here, to understand it effectively, for simplicity of understanding, let's use the displacement or a rotation type of a boundary condition. And once I select that, I'm going to go ahead and say continue. So then it asks me to select the regions for the boundary condition. As I already said, we're going to first do the bottom. So I'm going to go ahead and name that set as bottom. Once I name it, I also need to select the set here. So if I hold my cursor over the bottom edge, it's going to select this bottom edge here. So if I click on it, you see that's the bottom edge is highlighted. So I've done that. I've selected the bottom edge. I've also named it bottom. So I'm happy with it. I'm going to go ahead and say done. Okay, so then this dialog box is going to pop up now, where you can actually give in these values. So what we are actually going to impose a condition, a vertical boundary condition, which is to say u2 here. So one is the horizontal direction, two is the vertical direction here. So I'm going to go ahead and say u2. U2 is 0. So I'm going to select u2 and say okay. So then that's going to fix this bottom surface in that vertical direction. So that's what this boundary condition is going to do. So now we need to repeat the same procedure for the top uh, for the top edge. So I'm going to run over whatever we did just now. I'm going to run over it again. So I'm going to again go ahead and say create boundary condition, this menu icon here, and then click on it. And now it asks me to name. So I'm going to say top fix. We said bottom fix earlier. Now we are going to do the top fix. Again, a mechanical boundary condition, a displacement, and we are going to do it in the initial step. So then go ahead and click continue. It asks me to select the region for the boundary condition again. I'm going to name it top, and after naming it top, I'm going to select the top edge. So that's highlighted. The name is given here. So I'm going to go ahead and say done. Again, we just want to impose the condition in the vertical direction, so which is 2. So I'm going to go ahead and just check on u2. So this u2 is going to be fixed in this starting from the initial step for the top edge. So I've done that. I'm going to go ahead and say okay. You see these arrows come up in our window here. So that's an indication that we have imposed boundary conditions on the top edge in the vertical direction. That's the way the arrow is pointing, and also the bottom edge in the vertical direction. Okay, so then we are done with these two boundary conditions that we have already imposed that. What is left to do is to create these loads, an inner pressure of 50 megapascal and outer pressure of 30 megapascal. So let's go ahead and do that. That's the next logical step. So then now we go to this icon here or right at the top, the first row, which says create load. So I'm going to that's what we want to create. So I'm going to go ahead and click this, and these loads need to be defined in the pressurized step. As I said earlier, the fixed boundary conditions is what you typically would define in an initial step, but uh, these loads, which are basically the pressures that we are going to impose now, that we're going to create in the pressurized step. So I'm going to go ahead and select pressurize. It asks for a name, so I'm going to first do the inner pressure. So I'm going to go ahead and call it inner press, for just an acronym for the inner wall pressure. And now what we're going to do is, again, it's a mechanical type of a load that we want to impose. So we select the mechanical option here, and then you can impose these several different types of loads to the body. But what we want to do here is a pressure boundary condition. So we select this option for pressure, and once that is done, I'm going to go ahead and say continue. Okay, so then this instruction here asks me to select the surfaces for the load, and it's going to create a surface. So because we want to select the inner surface here, I'm going to go ahead and call the surface inner surf, uh, and select this left edge, which is the inner surface of the cylinder. I'm going to go ahead and do that. You see this is the inner edge is highlighted, and I've already named it inner surf. So I'm happy with that. I'm going to go ahead and say done. So then this dialog box now pops up, which is uh, which has these different options. So first, it's going to ask if the distribution is uniform. We are imposing a uniform pressure on this entire inner face. So the uniform default option is good. Magnitude, we decided to do a 50 megapascal inner wall pressure. So we need to give in that magnitude. As I said, we are working with SI units, so 50 E6. Just remember that. And for the amplitude itself, the default option is a ramp. We are happy to do that here. So what that ramp option basically is, it's going to ramp up this pressure value from an initial value of 0 at time is equal to 0 seconds, and we have decided to give it the entire analysis a total time of 100 seconds. So what the ramp is going to do is to linearly increase the pressure on the inner wall from 0 to this prescribed value of 50 megapascal over a time period of 100 seconds. So that's what it's going to linearly interpolate between these two values and ramp up the pressure uh, linearly. So that's what this ramp option is. We are okay to do that. So we're just going to leave it at those default options. I'm going to go ahead and say okay. So you see, once I hit OK, you see these arrows pointing, which says Abaqus has recognized that we have imposed a pressure boundary condition on this inner wall. So what I need to do next is again create another load now for the outer wall. So I'm going to go ahead and do that. Again, this option right on the top on the first row, which says create load. So I'm going to go ahead and click that. It's going to ask me for the name that I want to give it. So now I'm going to say outer pressure. So I'm going to call it outer press. It's again a mechanical load, and that is also a pressure type of a load. So I'm going to select mechanical and pressure, and then go ahead and say continue. Again, Abaqus wants me to do this all over again to select the surface for the load, and I can give it the name here for the surface that it's going to create. So because you're doing it on the outer surface, I'm going to call it the outer surf, and select this boundary, the right edge of the rectangle that we created, which is the outer wall of the cylinder. So I've done that. It's highlighted here in red. I've named it, so I'm happy with that. Going to go ahead and say done. Again, now we need to impose the outer wall pressure. So as we saw here, we decided to do a 30 megapascal outer wall pressure. So I'm going to enter that value in here. So I'm going to say 30 megapascal. So 30 E6. Again, the default options of uniform and ramp. We are happy with that. So I'm going to go ahead and say okay. So yeah, so that's it for the load module. We have you can see these arrows here. We have these two orange set of arrows, which are the two displacement boundary conditions that we have imposed, and these two sets of pink arrows, which are the inner and outer wall pressures that we have imposed. So that's all the boundary conditions that we need to give the body now. So we are done with everything regarding the load module. So I'm just going to quickly save it and move on to the next module. So we are nearing the end now. We are more than halfway through. We are going to move on to the mesh module now. Okay, so this is where we're going to mesh our body. So typically in a finite element simulation, you would discretize the entire body into these tiny finite elements over which the calculations are going to take place. The governing equations or the weak form of the governing equations are going to be solved. So we need to divide this body into these tiny finite elements. That's what we're going to do in this step. So we need to create the mesh on the part. So the object by default is selected on the assembly. We need to change it to part. So I'm going to go ahead and say part. We only have one part here, so Avix is automatically going to recognize that we're going to do it on this part, which we called cylinder. And you see this cylinder appear here. So what we want to do is discretize these edges and tell Abaqus how many elements, how many finite elements we actually need. So let me, as I keep going, it'll become more clear about what I'm saying. So I'm going to select this option, the second option on that first row, which reads seed edges. So that's going to allow us to create seeds on these different edges. So the seed is going to tell Abaqus, we are going to tell Abaqus that on each of these seeds, we actually want uh, nodes of those finite elements to actually appear. So I'm going to go ahead and say seed edges. So first, let's do the vertical edges. So I'm going to select the inner edge. So I'm going to click on it. It selected the inner edge, but I also want to simultaneously do the outer edge. So what you need to do is hold Shift and say and select the outer edge as well. So you can hold Shift and select multiple edges. So I already selected the inner one. I'm going to go ahead and click on this one as well. So I do that holding Shift. So then you see now both of them are highlighted in red. So both of them have been selected. So the regions should be assigned local seeds. I've selected these two edges. So I'm happy with that. I'm going to go ahead and say done. So so there are several different options of how you can mesh, how you can seed these edges. But the simplest one that I'm going to use now is going to do it by number. We'll tell Abaqus how many elements we want on each of those edges. So then instead of the default option by size, I'm going to go ahead and select by number. And what I'm going to do is uh, we actually know that we don't need too many elements in the vertical direction. Actually, the way the cylindrical problem is set up, there's not going to be any variation in our stress or strain fields in the vertical direction. All the variation is going to happen in the radial direction. So the vertical number of elements is not very crucial. So I'm going to give it a simple number of 30. Uh, so that's going to effectively create 30 seeds along each of these edges. So if I hit the number of elements 30, uh, with the default bias option of none. So then that's just going to create uniformly spaced elements, uniformly spaced seeds. And I'm going to go ahead and say OK. So you see these various triangles appear. So if you count, you'll have a total of 30 of them. So you'll have 30 different, this edge being split into 30 equal parts. So that's happened for both the left and the right edge of the rectangle. So now we also need to create seeds on the top and the bottom surface. So I'm going to the seed edge option is still active in Abaqus. So the dialog, the instruction here says select the regions to be assigned local seeds. So now I'm going to go ahead and select the bottom edge and again hold Shift and select the top edge as well. Uh, so I'm going to do both of them simultaneously, and I've selected both of them. I'm going to say done now. So you can scroll just as in any other program. You can scroll to zoom in and out of the part. That's what I'm doing here. Okay, so again, local seeds, it's going to ask us to seed by number. So we want to do it by number again. So I'm happy with that option that is active. But now, although uh, the size of the top and the bottom edge is about a half of the size of these vertical edges, we expect that there's more variation. Uh, there's more variation in the stress and strain fields in this radial direction. So because we expect that, I'm going to actually give it a slightly more number of elements, even though the size is smaller. So I'm going to say use let's use 40 different elements. So let's split these edges up into 40 different elements, and I'm going to say OK again. So you see now it's created this size is actually smaller than in the vertical edge, because that's what we prescribed. But now the top and the bottom edge have actually been divided into 40 different uniform sections, right? So then we have done the seeding. What I'm going to do now is to assign an element type to of what kind of elements we actually want to use in our material. So there is this option here on this fourth row, which says assign element type. So that's the one that I'm going to select. I'm going to click on this, and then the instruction asks me to select the regions to be assigned element types. Then I just hold my cursor over this part. So we want to assign the same type of element. throughout the body. So I'm just going to select on this, and the whole part is highlighted. Then I'm happy with that. I'm going to go ahead and say done. Okay, so then this huge dialog box pops up. So you can select various different types of elements. So the family is where you would say what kind of calculation you're doing. So here we're doing an axisymmetric static calculation. So the type of family is axisymmetric stress. You also have, if you're doing a lean thermoelasticity problem, so then you would select a couple temperature displacement type of an element and so on. But here we are just doing the default axisymmetric stress, which has already been selected. Uh, we're doing a standard calculation, so this is good. For the geometric order, I'm going to actually go ahead and say quadratic. So then if we select quadratic, what's going to happen is, let me go back to the linear. You see here, it says CAX4. So this is, AX is an indicator that we're doing an axisymmetric calculation. 4 is the number of nodes that we're going to have on each of these elements. But now if I go ahead and select quadratic, so then it's going to say AX8. So it also has a description which says it's an 8-node biquadratic axisymmetric quadrilateral. So this is going to be 8 nodes in each of these elements. So it's going to interpolate all our functions, do all our calculations much better than the linear geometric order. So I'm going to go ahead and actually use the quadratic geometric order for our calculation here. And also it's recommended, especially if you're doing plasticity sort of problems, to do the hybrid formulation and uncheck the reduced integration. So what the hybrid formulation does is, it's a better scheme for interpolation, especially in plasticity problems, as I said. But it's always good practice to use it even in this particular case that we're looking at. So I'm going to go ahead and say hybrid. So if you look here, uh, the the element code has actually, it has a CAX8H. H is basically to indicate that it's a hybrid element. Okay, so that's about it. You don't need to change any other options. So we're happy with what we've done. I'm going to go ahead and say okay. So if I hit OK now, all that's left to do is to actually create the different elements. So Abaqus has this simple option. So this option here, right here, it says mesh part. So that's what we want to do next. We want to create the mesh. So I'm going to click on this mesh part. So then it asks me, if I click on the mesh part, there's this instruction which asks me if it's okay to mesh the part. That's what I want to do. So I'm going to go ahead and say yes. So you see, if I select that mesh part, so then what happened here was it created these different tiny rectangular elements. So our entire body is broken up into these several finite elements over which the calculation is going to take place when we do the simulation. And you can also quickly see here that Abaqus instruction, it says, the dialog says 1200 elements have been generated, which is reasonable because we created 30 edges here and 30 partitions here and 40 partitions here. So it's created a rectangular grid of 30 cross 40, which is 1200 elements. So it's always cautious. It's always a good practice to be more cautious about the number of elements, because the more the number of elements, the longer your calculations would take. So you'd get a more refined solution with more number of elements, but the time for each of your calculations is also going to increase in accordance. So it's better to always start off with some reasonably low number of elements, and then if additional refinement is needed, you can go ahead and do more refinements. So here I'm happy with the 1200 elements that we have. So we are actually done with the mesh module. So we're almost there. The optimization module, you can do some special optimizations for how you want to solve the problems, but that's not necessary in this particular problem we are actually looking at. So I'm going to go ahead and look at the job module now. So I'm going to jump straight from the mesh to the job module. The optimization module, we don't need to we don't need to make any changes at all. So let's go to the job. So here is where you'd actually create a job, uh, which Abaqus will then run. So what I'm going to do is, what you need to do is first hit this option again on the first top row here, which says create job. So I'm going to go ahead and say create job, and it's going to ask me to name. So this is a thick wall cylindrical vessel that we are pressurizing. So I'm just going to simply call the I'm going to call the job pressure, right? So this model one is the model that we have just created, which we have gone through all these different modules. So this is the model one that we're working with. So that's already highlighted. So all you need to do is say name pressure and then continue, right? And then here you have this dialog box about where you can edit different options for the job. So there are these sub menus which say submission, general, memory, parallelization, precision. We don't need to worry too much about any of this at the moment. All of the default options are good to they're good to go to solve the problem of interest here. So I'm just going to go ahead and simply say okay. Yes. So now if you look at, so this thing here on the left is what is called a model tree. So it has information of everything that we have done so far. So if I so it has a part. So if I hit the plus here, so you see the part cylinder that we created. Under the material branch, you see steel, which is the material that we created, and so on. So all the information is actually here. So if I go ahead and say look at under the loads, it has the two loads, the inner pressure and the outer pressure that we created. It has these two different boundary conditions, the bottom, fixing the bottom, and the fixing the top face. So it has all the information of everything that we've done so far. And it's also created this job called pressure. uh, so now what we need to do is ask Abaqus to solve this job. So to do that, I'm going to open this again on on the first row, the second option here, which reads job manager. I'm going to go ahead and click it, and then that's going to show the jobs that we've created. Here we created this job named pressure, uh, and you have these several different options on the right, which say write input, data check, submit, monitor, and results. So what I'm going to go ahead and do is first, it's always good practice to do data check. So when we do the data check, what Abaqus is going to do is to see if all the boundary conditions that we impose for this problem are actually self-consistent. Uh, so it's a good practice to always do that before you actually submit and solve the entire job. So so I'm going to go ahead and hit on data check. So then Abaqus is going to do the data check. You see the status here. It says check submitted. Then it's actually running the check now. uh, so we just need to wait for it to come back. Okay, so the status now says check completed. That means Abacus is happy with everything that we have done. So everything is self-consistent, so it's happy, and it says check completed. If something was wrong, it would say aborted, or there's an error in the status under the status menu. So we're good with what we've done so far. So I'm going to go ahead and say submit. So if I say submit, that's going to uh, that's going to solve the system that the boundary value problem that we just defined in Abacus. So it says job file already exists for pressure. That's because we just did a data check, so it already created some of those files. It's asking me if it's okay to overwrite. We are okay to overwrite those. So I'm going to say okay, and then now Abacus is going to solve this problem for us. So it says status submitted. So Abacus is the job has been submitted. Now the calculation is running. Abacus is trying to solve the particular problem for us. So we just need to wait for some time. Okay, so Abacus says status completed. That means it finished solving. So now we are going to go ahead and look at the results. So let me hit the results tab here. Um, if we hit the results tab again on this option on the right, if I'm going to go ahead and click, and then it's going to open up just in a moment. It's going to open up uh, the job that it solved. So you see here, uh, right now this is what has been selected. If I hold my mouse over it, it says plot undeformed shape. So this is just the body that we created. What we actually want to do to look at the contours of the various fields is select this option at the bottom, just below this highlighted option, which is plot contours on deformed shape. So let me go ahead and do that. So if you do that, it says you can see these contours that start to appear, and it says stress meses. So it's plotting is actually the meses stress. And remember, we gave it our steel yield stress of 300 megapascal. You see here, it says 4.686 E7, so that amounts to about 46.8 or about 47 megapascal, the which is the meso stress here. Our meso stress is clearly well below the yield limit of 300 megapascal. So roughly about, if you do 300 over 50, is roughly a factor of safety of 6. So right now our pressure vessel is far away from yielding. So so that's good. We can actually increase the loads roughly about a factor of 5 or 6 before it starts yielding. But right now there's no yielding in our body, which is good. But we can also look at some other uh, some other interesting parts of the solution. So if I go back to my presentation, so if we from the text for the course, we had an analytical solution for this thick wall cylinder problem. So in there, the sigma theta theta, the stresses in the the theta theta component of the stress as a function of the radial coordinate was actually given by this expression. Uh, so in our case, we had B by A. Our outer radius was 200 millimeters for the cylinder. Inner radius is 100 millimeters. Let me quickly show that. So it's an outer radius of 200, inner radius of 100. So then B by A is actually 2. So that's the new number that we have in our case. And internal pressure of 50 megapascal, outer pressure of 30 megapascal. So if I plug in these numbers, then at the radial coordinate A, which is at the inner wall, uh, sigma theta theta is expected to be 10 over 3 megapascal, and at r equal to B, it's expected to be minus 50 over 3 megapascal, right? So then let's go ahead and look at what our Abaqus solution tells us. So as I said, one here is the horizontal direction, which in the cylindrical coordinates is the r coordinate. 2 here is this vertical y direction. 2 here is this, which in the cylindrical coordinates uh, is the axial coordinate, which we typically represent by z. And 3 here is the coordinate into this plane of the screen. So 1 is horizontal, 2 is vertical, 3 is the coordinate into the coordinate direction into the plane of the screen. So that is effectively our theta direction. So what we want to look at is actually S33, right? That's the theta theta. That's the analytical solution that I just showed you on the PowerPoint presentation. So that's the value that we want to look at. So let me open up S33, and now if I do that, let's look at what happens at the inner wall. At the inner wall, you see here the stresses. Abaqus tells me it's red at the inner wall. So Abaqus tells me the red value is about 3.33 megapascal. So if I go back to our solution here, sigma theta theta at r equal to a is 10 over 3, which is 3.33 megapascal. So Abaqus has picked it up pretty well. And on the outer surface, which is blue, the extreme is the extreme of the blue legend here, which says minus 16.67 megapascal. Right now, if I also look at sigma theta theta at r equal to b from our analytical solution, it was minus 50 over 3, which is the same as minus 16.6666 megapascal. So our Abaqus solution, in fact, matches really well with what we expect from our theoretical solution, the analytical solution that we had in the book. So now back in Abaqus, we can also look at in this drop-down menu of the contours of stress. So we can also look at the maximum principal stress. So if you plot the maximum principal stress here, the maximum positive value here is only about 3 megapascal, and that happens at the inner wall of the cylinder. So typically when you're trying to see if the material can fail by fast fracture, it's the max principal value that is of interest. For steels, depending on what the flaw size is, this could be this number, the max principal stress at which failure can occur could vary, but it's expected to be of the order of a few hundred megapascals. Here we are only about 3 megapascals on the inner wall, so we expect that this particular pressure vessel is going to be safe for operation. Okay, so now we can also look at the stresses in the vertical direction, in the 2-2 direction. You see here, the contours are, it's nearly homogeneous state of stress in the vertical direction. It's about a 15.4 megapascal of stress. So remember, we actually imposed plane strain conditions on the bottom and the top face. So we constrain the bottom and the top face from moving in the vertical direction. So the stresses, that's why you see these stresses develop in the vertical direction. But if I now go ahead and look at these, change these contours from S, which is the stress, change it to strain E, and I look at the 2-2 direction strains E22, you see these are of the order of 1E minus 18, which is really, really small. So effectively the strains in the vertical direction are zero, because that's the kind of class of problems that we are looking at, the plane strain cylinder. So the strains are zero, whereas the stresses itself in the two direction, again going back to the S22 contour, you actually see a compressive stress of about 15.4 megapascal developed within the cylinder. Let me also go back to the strain contours and show you what the strains in the radial direction look like. So E11 is the horizontal direction, which is the radial direction in our problem. So you see the strains are of the order of 1E minus 4. So they are quite small strains. So our small strain assumption here is in fact justified. And we can also look at the strains in the 3-3 direction, which represent the hoop strains. The hoop strains are also of the order of 1E minus 4. They're quite small. Uh, so the fact that the deformation here is small, we can also look at it from the displacement contours, which is U. U stands for the displacement. So if you look at the magnitude of the displacements, it's of the order of 1E minus 5. And if you remember, our cylinder itself has a overall dimension of the order of 200 millimeters. So that's of the order of 2E minus 1. So that's about 2E minus 1. So the displacements are in fact about 4 orders smaller than what the size of the specimen is. So which is good to know that our small strain assumptions are in fact valid in this scenario. And what Abaqus also lets you do is to look at this deformation. So let me show you a couple of other tricks here in Abaqus. So uh, here there's this option on the sixth row on this menu here. So there is this option which, if I hold my cursor over, it says allow multiple plot states. So now I'm going to select this particular option and say allow for multiple plot states. So then this is going to allow me to plot two things simultaneously. And what I'm going to do is now go ahead and click on this icon on the third row which says plot undeformed shape. And I'm also going to plot the one right next to it, which is the plot deformed shape. So I just want to plot the undeformed and the deformed contours together. I'm not interested in looking at the colored contour variation, so I'm going to select on that and just unclick it. Uh, so once I do that, here what's actually happening is there are two sets of contours, which is the original specimen that we started off with, and this particular option which says the deformed shape, that's going to plot the specimen taking into account the displacements and effectively the deformation of the cylinder. But here you see it's very hard to differentiate between the two of them because the displacements are really small. So we're not able to distinguish between what we started off with and what the deformed cylinder looks like. So what we can also do in Abaqus is to blow up these displacements. So we can magnify the amount of displacements within Abaqus and then show you how to do that. So if we go to this option on top, the menu which says options. So if I click on that, there is this first option which says common. So I'm going to go ahead and select common under this options menu, and then this dialog box is going to pop up. So here you have several different sub menus that we can explore, but what I'm interested in is to look at this deformation scale factor field. uh, So in this dialog box, right now we have been working with a uniform deformation scale factor of 1. So that's why, because the displacements are so small, we are not able to see these displacements. Now let's say I change it up to a factor of 1,000. What's that going to do? What that is going to do effectively is to magnify the displacements by a factor of 1,000, and the deformed contour is now going to be plotted using these magnified displacements. So if I go ahead and say apply here, you see here, now we start to see these two distinguished contours. So the gray contour of the background is what we plot by this menu, which is the undeformed shape. So that's the original cylinder that we started off. You see the gray contour here on the left, and this is where the outer wall is on the gray contour. But the green contour is what we plotted using this sub option, which says plot deformed shape. uh, so clearly, because we are applying a pressure on the inner wall as well as on the outer wall, the it has led to effectively a radial contraction of the cylinder. Of course, we have magnified it 1,000 times to look at it better, but effectively there's some radial contraction of the cylinder. So the inner wall has moved away away from the undeformed edge here, from the gray contour, and even on the outer wall, it has moved away uh, from the undeformed contour, which is shown in gray. So Abaqus lets you do all of these things. Uh, However, now let me zoom out slightly, and then we can see what's happening at the top, because we impose the plane strain conditions, irrespective of how much we are blowing up our deformations by. You see, because we have set it to 0, so irrespective of how much we magnify it, that that displacement is going to be 0. So the bottom and the top edges are still at the same vertical level as the bottom and the top edges in the deformed specimen are still at the same vertical level as the undeformed specimen. Okay, so that's another useful trick in Abaqus. Now I'm going to go back and just say a value of 1 and apply, because we're happy with what we've looked at, and say OK. I'm also going to unselect this allow for multiple plot shades. I want to go back now and show you the contours again, with the stress contours. So let me go to the plot, hit this option, which is plot contours on deform shape. So I only want to look at that one. Let me also go back to the stress contours, which is S standing for stress. And I want to look at the S33 component, the stress in the 3 direction. So as we just discussed, the stresses here from Abaqus match really well with what we expected from an analytical solution. However, that might not always be the case. Here, we use 40 elements, and we used a quadratic type of an element in our mesh. So these numbers seem to match exactly. Now, what I'm going to show you is how we can quickly change the mesh and how that's going to change these comparisons. So let's go back now under this module, on this module menu. Let's now go back to the mesh module. I want to remesh it with a slightly different mesh and show you what happens. So I'm going to go to the mesh menu, mesh module, and we are in here in the mesh module. I want to change it from a quadratic type of an element to a linear element. So then remember what we did again when we were doing the meshing. We hit this option which says on the 4th row, which says assign element type. So I'm going to select that, and then the instruction asks me to select the region to be assigned element types, which I'm going to select this whole body that's highlighted. So I want to change it for the whole body. I'm going to say done. And remember, we used a geometric order of quadratic. Now I'm going to show you what happens if you change it to a geometric order of linear. So let's switch to linear. Let's still try and stick to the hybrid formulation. So I'm going to check the hybrid box and get rid of the reduced integration. So we're going to do, the only change we have effectively made is gone from quadratic to linear, and we're still sticking with the hybrid formulation. And then I'm going to say, okay. So then these elements have now, we have told Abaqus to actually solve it using linear elements rather than quadratic elements. And that's the only change I want to make at this point. And if I do that and now go back to our job module, I'm going to try and open up this job manager. This is how we did it last time. This second option on the first row, which says job manager. I'm going to open it. Uh, and now I'm going to submit this job again so that we can resolve it using the linear elements. So I hit submit, It asks me whether it's okay to overwrite. I'm happy with that. I'm going to say okay. And now Abaqus is going to solve this problem again for us. So let's just wait till Abaqus gives us the solution. So it's still, the status still says running, right? So now the status is completed. So then Abaqus is ready with the solution for us to look at. So I'm going to go ahead like we did earlier. I'm going to say this, click on this results option. So that takes me to looking at these results. So now I'm going to go back to the colored contours, and I want to look at the S33 contours. So now you see the stresses on the inside have actually gone from 3.33 megapascal to about 2.7 megapascal. And then on the outer, there's a much smaller variation. It's gone from 16.66 megapascal to 16.58 megapascal. So you see, because now we went from quadratic to linear, Abaqus is not doing as well a job interpolating the solution. So the solutions are slightly different from what it's about 10 or 15% different from what the theoretical solution is. So that's something that we definitely need to exercise caution when you're working with Abaqus. It's about how well you're if on whether your finite elements is resolving the problem enough to actually get a reasonable solution that you can make physical sense of. So what we can do is, because we are here trying to look at what's happening on the inner and the outer wall, so even with this setup with the linear elements, I'm going to go back to the mesh module. So here on the module again, I'm going to go to the drop down list and select mesh. So now I'm going to change how we seeded these horizontal edges, which is the top and the bottom edge. So I'm going to go back to the seed edge option. I'm going to say seed edges, right? I'm just going to click on it once, and then I'm going to select the bottom edge and hold shift and select the top edge as well. So I've selected both these edges. Then I say done. Earlier we had no biasing in our system. So now I'm going to change it to select this option of double biasing, which I'll tell you in a moment what it is. So I'm going to say double biasing, and then I'm going to select a bias ratio of 10. And once I do that, I'm going to say okay. So it's asking me whether the older mesh can actually be deleted. So I'm happy with that. It's okay. I'll be happy to remesh it. So I'm going to say delete mesh. So now you see what we have done effectively is, through this double biasing, we have actually refined. You look at the element spacing here. Earlier we had uniform element spacing across the entire edge, but now you can clearly see the spacing between two successive seeds here, right close to the center of the specimen, is much larger than what it is at the edge of the specimen. So we have effectively prescribed a bias of 10. So this distance between the subsequent the distance between successive seeds is actually 10 times higher at the middle of the edge than as compared to the to left or the right side of the edge. So I've done this because we want to resolve the solutions better at the two edges, and this is the same case on the bottom side as well. Okay, so now with this seeding, let's try to mesh our specimen again. So I'm going to hit this option which says mesh part. It's asking me whether it's okay to mesh the part. That's what I want, so I'm going to say yes. And now it created this mesh where you can clearly see it's almost square here towards the middle of this specimen, whereas on either the inner and the outer radial end, the aspect ratio of the elements are much different than a square which has a 1:1 aspect ratio. Okay, so now we have done this. Now let's try and go back to our job module, right? And we still have the job manager open. So I'm going to submit it again, ask Abaqus to solve it one more time for us with this updated double bias mesh. I'm going to solve the system again. So Abaqus is doing it. It's telling me it's running the calculation. Okay, so it says now the status has changed to completed. So Abaqus is ready with the results. So I'm going to hit the results option. Okay, so now let's look at the colored contours again and look at the three stress components. You see now it's gone back to pretty close to what the analytical solution is. So the analytical solution, remember, is 3.33 megapascal. Now it's gone from earlier we had 2.7 megapascal with the linear mesh. Now because we've resolved it well enough at the boundaries, uh, it's gone back to about 3.17. So that's a much smaller error than what we had earlier. And on the outside, it almost matches it almost matches exactly with what the analytical solution. So the analytical solution was 16.66 and minus 16.66 megapascal. Now it's become minus 16.65 megapascal. So definitely always keep an eye out on how well you're resolving the problem, to dig out the physical field of interest that you're looking at. So that's very important when we're doing these class of boundary value problems in Abaqus. Okay, I'll show you one more trick here. Here we are actually simulating a cylinder, but all we are looking at here is this rectangle. So it's very difficult to visualize what it looks like. So let me let's look at the uh, Mises stress contours. Uh, so now I want to be able to show you how to actually look at a cylinder. Abaqus gives you that option because we have done an axisymmetry calculation. What you can actually do in Abaqus is go to the second option on the second row, which says ODB display options. I'm going to click on that, and then this dialog box pops up with these various submenus. So I'm going to so these are general, entity, display, constraints, mirror pattern, sweep, extrude, and so on. So I'm actually going to select this sweep extrude option. So we're going to sweep. What we're going to do is sweep this rectangle uh, around about the axis of symmetry that we created, so that we can actually visualize the cylinder. So then I'm going to say sweep elements, and we want to sweep the whole cylinder. So we're going to say from 0 to 360 degrees, and I'm going to be able to have a good visualization. It's good to have a large number of segments. So 36 is what I found usually works well. So let's say we want to use 36 segments. So I'm going to say 36, and once I do that, I'm going to say okay. You see what's happened here is Abaqus has actually created a cylinder. So how you can look at that is go to this option right at the top here, and if I hold the cursor over it, it says rotate view. So I'm going to hit that rotate view, and once I do that, this the cursor changes to this rotation symbol, and once that is the case, we can click and move our mouse to actually rotate the body. So now if I rotate the body, you see here the Mises stresses contours. Now you have a radial distribution you have across the entire cylinder, which we are now visualizing. Across the entire cylinder, you have on the inner wall there are the highest Mises stresses of about 47 megapascal, and on the outer wall the Mises stresses drop to about 14 megapascal, and we can actually visualize the entire cylinder that we were working with. So that's another very useful tool that Abaqus gives us in these axisymmetric class of problems. So there are a lot more things that we can actually do with Abaqus within the in this visualization window. So we're going to see some of them as we progress along in our future Abaqus tutorial videos. Okay, so I'm going to reopen this ODB display options and get rid of the sweep. So that let's go back to the rectangle. So I'm going to say apply. I'm going to say okay. And now if you want to go back to the XY view that we had, the just the planar view, there's this simple option on Abaqus which says it's very descriptive. It says X and Y on these two axes. So if I if I click on that once, it goes back to the view that we were initially working with. So that is good. Uh, so now what we had done so far is all on the plane strain cylinder, right? So we were looking at this problem where we had a vertical constraint on the bottom as well as the top edge. But now let's look at the other case with an unrestrained cylinder. This is the case that these are the set of boundary conditions you would expect, like when you try to use a piston cylinder assembly. This is an unrestrained cylinder case where there are no longer any displacement restrictions on the top and the bottom edge in the vertical direction. It's in fact actually traction free on those top and the bottom faces. So let's try and see how I'm going to show you how we can model this using the CAE model that we just created. It's actually pretty simple to do this. So now from our visual, now if I go back to CAE and then from our visualization module, I'm going to go back to the load module, which is where we need to make our changes. So uh, here what I'm going is, you see these are the boundary conditions that we have currently imposed. You see these orange arrowheads here, which are saying that these are on the bottom and the top edge, which are basically saying we on the bottom and the top edge we have constrained the vertical direction motion. But what now I'm going to do now is to actually get rid of this constraint on the top, because we want to model the unrestrained cylinder. So on the top fix boundary condition, I'm going to right click uh, on that, and then these various different options pop up, and I'm going to say suppress. So if I say suppress, then you see here now in this window that uh, initial constraint that we had on the top face, we've gotten completely rid of that. Now there's no longer a constraint on the top face that's constraining it from moving vertically. Okay. However, we still want the bottom constraints to remain in place, because if we get rid of all the constraints in the vertical direction, then the cylinder will actually be able to move vertically freely. It's like a rigid body motion that we are introducing. So we do not want the cylinder to just fly away in the vertical direction. So we still have to impose some sort of a constraint on in the vertical direction, even to model the unrestrained cylinder. So we're going to leave this boundary condition on the bottom. We're going to leave it in there just to avoid any rigid body motions. So then once I do this, I can go back to our job module. uh, Here in the job manager, I'm going to submit it again, just one more time. Last time I'm going to say submit. I'm just going to say okay to overwrite, and then let's wait for Abaqus to solve this problem now. Okay, so let's go in and look at the results. I'm going to hit this results button. Okay, so remember, this is now the case of the understrained cylinder. So let me hit this, look at the colored contours, and let's actually look at S22, which is stresses in the vertical direction. So you see here from the legend, you see the stresses are only of the order of 1e minus 7. And remember the pressures that we applied in SI units, they are of the order of 1e6 Pascal. And so the stresses in the vertical direction in these contours here are about 12 orders of magnitude smaller. So these are just numerical perturbations, and effectively the stresses in the vertical direction is 0, which is what we would expect because there are no longer any constraints in the vertical direction. So we've allowed it to, because it's unrestrained, basically we've not imposed constraints on the top face. So we have allowed it to expand, and there's no, the top face itself is traction free, and that's why we see the vertical stresses are in fact quite close to 0. So in this case, if my now go in and look at the strain contours, which is the E, and I want to look at the 2-2 component, you see here the strains now in the 2-2 direction, the vertical component is actually homogeneous throughout the body, and it has a magnitude of about 7.7 E minus 5. So that's a positive strain in the vertical direction. So that's basically saying there's expansion in that direction. And in our earlier case simulation with the plane strain cylinder, what we had was we had 0 strain because we didn't allow for any motion in that direction because of our constraints. But now in the understrain cylinder case, uh, because we have gotten rid of the constraint on the top face, you see there is a tendency for the cylinder to actually expand radially. And that's because as we have applied pressures on the inner and the outer face, that's effectively leading to some contraction in the radial direction. And due to the Poisson's effect, it results in some expansion in the vertical direction. So I guess, yeah, that's it for the unrestrained cylinder, and that brings us to the end of uh, this particular the first tutorial, Abaqus tutorial on the thick walled cylinder. And thank you for watching.